For 4 centuries, moon has meant something dead. A frozen rock. No weather, no activity, no chemistry worth mentioning. Europa doesn't fit that definition. It hides a global ocean holding twice as much water as every ocean on Earth combined. Its surface is young, resurfaced again and again, not by wind or rain, but by something moving underneath it. Its ice bends and flexes and drips. A new study suggests that ice may even be sinking, carrying surface material down into that ocean, the same way tectonic plates recycle Earth's crust. Moons don't usually do that. Worlds do. So maybe the question isn't what's inside Europa's ocean. Maybe it's whether moon was ever the right word for it at all. Let's find out. Europa is the smallest of Jupiter's 4 large moons. It's slightly smaller and less massive than Earth's own moon. You could see it tonight with a pair of ordinary binoculars if Jupiter is in the sky. But the resemblance to our moon ends almost immediately. Where our moon is grey, cratered, and geologically dead, Europa is pale, young-looking, and strange. It has almost no large craters, just an icy shell wrapped in thousands of miles of cracks, ridges, and reddish streaks, some of them stretching more than 600 miles across the surface in long, curving arcs. For a solid object floating in space for 4.5 billion years, that's not normal. Something has been erasing Europa's history and writing a new one, over and over again. Now, here's the part that makes this more than a curiosity. Beneath that ice, scientists are fairly confident there is an ocean. Not a small one. Europa's global ocean may hold roughly twice as much water as every ocean on Earth combined. And where there's a warm, salty ocean sitting on top of a rocky seafloor, there is at least the possibility, not the certainty, but the possibility of something living in it. That's why this small, icy world keeps showing up at the top of NASA's list of places to search for life beyond Earth. And it's why, on October 14th, 2024, a spacecraft called Europa Clipper lifted off from Kennedy Space Center on a Falcon Heavy rocket, beginning a 5.5-year journey to go find out. But to understand why scientists are so interested in what's happening under Europa's ice, you first have to understand a problem that has puzzled them for over 2 decades. A problem about a barrier, and a very strange proposed answer for how that barrier might not be a barrier at all. Europa orbits Jupiter in just over 3.5 days, at a distance of roughly 670,900 kilometers, tracing a nearly perfect circle around the giant planet. Like the other large moons of Jupiter, it's tidally locked, meaning the same hemisphere always faces inward, toward Jupiter, the way our own moon always shows Earth the same face. That should, in theory, make Europa's orbit calm and predictable. But it isn't. Quite. Europa's orbit is kept very slightly elliptical, not by chance, but by a gravitational tug-of-war with its neighboring moon, Io, in what's called an orbital resonance. That small eccentricity means Europa's distance from Jupiter is constantly, if subtly, changing. And because Jupiter's gravitational pull weakens and strengthens as that distance shifts, Europa's entire body is repeatedly stretched and released, squeezed in, allowed to relax, squeezed in again. This is tidal flexing. And it's the quiet engine running underneath everything else in this story. It's the reason Europa's interior stays warm. It's the reason its ocean hasn't frozen solid over 4.5 billion years. And, as you'll see, it may be the reason the moon's icy shell never gets the chance to sit still long enough to simply stay strong. The first hard evidence that Europa was hiding a liquid ocean at all didn't come from a camera. It came from a magnetometer. When NASA's Galileo spacecraft made 12 close flybys of Europa between 1995 and 2003, its instruments detected something unexpected: an induced magnetic field, one that shifted in step with Jupiter's own enormous magnetic field sweeping past the moon. Europa has no magnetic field of its own. but something inside it was conducting electricity well enough to generate one anyway. The leading explanation, still favored today, is a global layer of salty liquid water sitting not far beneath the surface. Scientists searching for life beyond Earth generally look for three things: liquid water, chemistry, and energy. Europa seems to have all three. The water is the ocean itself. The energy comes from something called tidal flexing. As Europa orbits Jupiter, the giant planet's gravity squeezes and stretches the moon's interior the same way repeatedly bending a paperclip generates heat. That flexing is thought to be strong enough to keep Europa's ocean liquid despite the moon's extreme distance from the sun, and it may also heat the rocky seafloor enough to drive hydrothermal activity similar, perhaps, to the vents discovered on Earth's ocean floor back in 1977. A discovery that reshaped our understanding of what life needs to survive. The chemistry is where things get complicated. Europa's surface is constantly bombarded by radiation from Jupiter's intense magnetic field. That radiation splits apart water molecules in the moon's extremely thin atmosphere. The hydrogen, being light, drifts off into space. The oxygen, heavier and more reactive, tends to stay behind, embedding itself into the icy surface as oxidants, chemically hungry compounds that could, in principle, provide the kind of energy source a simple organism might use to survive in permanent darkness, the way it does for microbes buried far from sunlight here on Earth. So, the ocean has water, the interior has heat, and the surface has fuel. But there's a wall between the fuel and the ocean, and that wall is the ice shell itself. Nobody actually knows how thick Europa's ice is. Estimates run anywhere from just a few kilometers to 20 or 30 kilometers, depending on which model you trust and which kind of ice rigid or slowly flowing you're accounting for. Some studies have put the total water ice layer, cracked crust plus liquid ocean beneath, at around 100 kilometers deep in total. And that ice, however thick it turns out to be, is very good at doing exactly what a wall is supposed to do. It keeps things out. So here is the actual mystery driving Europa research right now. If the surface has the fuel, and the ocean has the water and the heat, how, if at all, does the fuel get down there? For a long time, researchers have proposed a handful of possible routes. One idea is the simplest: cracks. If a crack forms that runs the entire depth of the ice shell surface to ocean, then surface material could theoretically fall or be flushed straight down. The problem is that a shell-spanning crack is mechanically difficult to create. The top of the ice is rigid and brittle. The bottom is warm and stretchy. Getting a fracture to propagate cleanly through both is like trying to crack a pane of glass glued to a sheet of taffy. The physics resist you at exactly the seam where the two layers meet. Another idea involves convection, the same process that moves hot and cold currents in Earth's mantle. If Europa's ice shell behaves like a slow-moving fluid, warm ice could rise from the bottom and cold ice sink from the top, carrying surface material downward as part of the cycle. The trouble is that the very top layer of the ice, the part actually exposed to space and loaded with those radiation-made oxidants, is thought to be too cold and too rigid to get pulled into that circulation at all. In the language planetary scientists use, Europa's ice shell convection is stuck in what's called a stagnant lid regime. The lid doesn't move. It just sits there, sealing everything in. A third, and more recent idea, published in 2022 by a research team led by geoscientist Mark Hess, proposed that pockets of salty water brine trapped within the ice could migrate downward in slow-moving pulses called porosity waves, briefly widening tiny pore spaces in the ice to seep through before sealing shut again. Their models suggested that a striking amount of Europa's surface oxygen, potentially more than 80% of it, might make its way to the ocean this way over the course of thousands of years. It's an elegant idea. But it depends on the ice underneath the brine already being partially melted, which may only happen in specific places, like the strange, jumbled terrain scientists call chaos regions. None of these mechanisms is wrong, exactly. They're just each limited. Cracks are rare. Convection doesn't reach the surface. Brine percolation needs pre-melted ice. It helps, at this point, to actually look at what Europa's surface is telling us, because the ice itself seems to be recording evidence of all of these processes happening somewhere, at some point. Crisscrossing the entire globe are the reddish-brown streaks called lineae longue, curving lines where the crust on either side has visibly shifted relative to itself, some running for more than 600 miles. The leading explanation is that these are places where warm ice erupted upward as Europa's crust slowly spread apart, not unlike the way new crust forms along Earth's oceanic ridges. If that's true, then somewhere else on Europa, old crust has to be going down to make room for the new material spreading outward. Scientists call these sites of convergence subsumption bands, and mapping efforts, starting with researchers Simon Kattenhorn and Louise Proctor in 2014, later expanded by other teams, have identified regions where this kind of surface convergence appears to be genuinely happening. Elsewhere on the surface are features called lenticulae, Latin for freckles. Some are domes, some are pits, some are smooth dark spots, and some are jumbled chaotic terrain, craggy ice blocks embedded in rough, hummocky material, looking almost like icebergs frozen mid-collision in a churning sea. One well-studied example, called Connemara Chaos, shows peaks nearly 250 meters high, standing next to smooth, flat plates, as if a section of crust had simply broken apart and refrozen at odd angles. Chaos terrain like this covers roughly a quarter of Europa's entire visible surface. Some researchers think it forms above shallow, localized pockets of liquid water sitting just a few kilometers under the ice, distinct from the deep global ocean further below, warmed just enough by convective upwelling to partially melt the base of the shell above them. All of this tells you that Europa's crust is active, young, and constantly being rewritten. What it doesn't tell you, on its own, is exactly how the fuel on the surface gets down to the ocean underneath. And then, in January of 2026, two researchers, A.P. Green and C.M. Cooper, publishing in the Planetary Science Journal, proposed something different. Something that didn't require a crack, didn't require convection to reach the surface, and didn't require the ice to already be melting. They proposed that under the right conditions, Europa's surface ice can simply drip. Before going further, it's worth understanding exactly where this proposed fuel on Europa's surface actually comes from, because the process is almost violent. Europa sits deep inside Jupiter's magnetosphere, and as a result, its surface receives a daily radiation dose that would be lethal to a human being exposed for even a single Europan day, roughly 5.5 sieverts, an amount high enough to cause severe illness or death within about 24 hours of unshielded exposure. That radiation, made up of high-energy charged particles trapped in Jupiter's magnetic field, continuously slams into Europa's icy crust. When it does, it tears water molecules apart. This process, called radiolysis, splits H2O into hydrogen and oxygen. The hydrogen, light and fast-moving, escapes Europa's weak gravity and drifts away into space, forming a faint halo of gas that both Cassini and Galileo detected orbiting along Europa's path around Jupiter. The oxygen, heavier and more chemically reactive, tends to stay behind, embedding itself into the icy regolith, sometimes trapped in tiny bubbles within the ice itself. Over time, thousands, potentially millions of years, this process could build up into a genuine reservoir of oxidants sitting in Europa's uppermost ice. Not just molecular oxygen, but related compounds like hydrogen peroxide, all of it representing stored chemical energy, the kind an organism adapted to darkness might, in principle, be able to use the way we use oxygen ourselves. One estimate places the total surface oxidant inventory somewhere between roughly 400 trillion and 5.6 quintillion moles of O2, a range so wide it spans 4 full orders of magnitude, which tells you just how little is actually pinned down here. The problem, again, is that all of this fuel is trapped at the surface, sitting on top of a barrier of ice that separates it completely from the one place it could actually be put to use. To understand what dripping means here, you have to go back to Earth first, specifically to places like the Sierra Nevada and the Andes. Beneath large mountain ranges formed by volcanic activity, geologists have long observed a strange process. As magma rises and cools beneath these mountain belts, it leaves behind a dense, heavy residue at the base of the crust, something like the sediment left at the bottom of a boiling pot. Over time, this dense root grows heavier than the material around it. And eventually, under its own weight, that dense root detaches and sinks, plunging down into the mantle in a slow-motion process called lithospheric delamination, or more informally, dripping. This isn't a sudden collapse. It's not an earthquake. It's a gradual, viscous process, more like a lava lamp than a landslide. The dense blob stretches, narrows, and slowly falls, dragging surrounding material inward as it goes. Green and Cooper's question was simple, on paper, and audacious in practice. Could the exact same physics, the same equations that describe a mountain root sinking into Earth's mantle, apply just as well to a moon made of ice? To find out, they built a computer model using a geodynamics simulation engine called Underworld, software that has previously been used to study the interior of Venus and the behavior of terrestrial ice sheets. They constructed a virtual slice of Europa's ice shell, 30 kilometers thick, cold and rigid on top, warm and slowly flowing underneath, just as thermal models of the real moon suggest. Then they asked, what happens if a patch of that ice is a little saltier and a little weaker than the ice around it? Here's what you need to know about salt in ice, because it does something unintuitive. Salt makes ice denser. That part is straightforward. Dissolve salt into water, freeze it, and the resulting ice weighs slightly more than pure ice would. But the more important effect, the one that turned out to matter most in this study, is that salt makes ice weaker. Studies of sea ice on Earth show that salt-enriched ice is far more vulnerable to fatigue. Repeated flexing and stress can crack its internal structure and reduce its strength by half or more. Salt grains embedded in the ice's crystal lattice also block ice crystals from growing large and strong, keeping the grain size small, and small-grained ice, it turns out, can be dramatically less viscous, meaning it flows and deforms far more easily than coarse, pure ice. Europa is a moon under constant tidal stress. Jupiter's gravity flexes it continuously, the same flexing that generates its internal heat. Green and Cooper's reasoning was this: if patches of Europa's ice are enriched in salt, and there's real evidence they are, based on reddish, salt-associated coloring spotted by the Galileo spacecraft and the Hubble Space Telescope in regions that line up with known zones of surface compression, then those patches would be both heavier and weaker than the ice around them. A dense, soft spot sitting inside a cold, rigid shell. That is exactly the setup needed for a drip to begin. So they ran the simulation, and it worked. Every single model configuration they tried, and they tried dozens, varying the salt content, the weakness of the ice, the size and shape of the salty patch, resulted in surface ice successfully sinking all the way to the base of the shell. But it's the how fast that should really stop you. On Earth, this kind of lithospheric dripping mountain roots sinking into the mantle takes hundreds of millions of years. It unfolds across spatial scales of hundreds to thousands of kilometers. It is, geologically speaking, glacial, which makes sense, since it's happening in solid rock roughly 1 billion trillion times more viscous than warm honey. In Green and Cooper's ice models, the fastest cases completed the same basic process: surface ice, sinking to the base of a 30-kilometer shell in as little as 30,000 years. Read that again. Not 30 million years, 30,000. That's not a typo, and it's not a rounding error. It's the direct result of a simple fact. Ice is dramatically less viscous than rock. Typical ice viscosities are estimated at around 100 trillion Pascal seconds, while the rock inside Earth's mantle, specifically a mineral called olivine, resists flow at viscosities millions of times higher. Weaker material moves faster under the same gravitational pull, even in the slowest, most resistant model cases Green and Cooper tested. The full sinking process took somewhere between 1 and 15 million years, still a blink of an eye compared to the terrestrial version of the same phenomenon. Why does that number matter so much? Because Europa's entire visible surface is thought to be somewhere between 40 and 90 million years old, remarkably young for a solar system object. Whatever is resurfacing this moon is working on a timescale that's fast by planetary standards, and a delivery mechanism that operates in tens of thousands to a few million years fits comfortably, even conservatively, within that window. Other tectonic processes proposed for Europa, like the slow spreading of icy bands, are estimated to work on scales of roughly 1 million years. Icy dripping, in its most efficient form, could be dozens of times faster than that. The behavior itself, once it gets going, has a strange, almost organic shape to it. In the model, the process always starts the same way. A dense, weakened patch of ice, Green and Cooper called it the drip nucleus, begins forming a bulge at one edge. That bulge quickly falls to the base of the shell and then migrates sideways until it settles at the center of the weak zone. From there, the interior of the salty patch continues draining downward, steadily, like sand through the narrow part of an hourglass, until only the top kilometer or two of surface ice remains. Then, something interesting happens. That remaining surface ice, the part that had been sitting exposed to space, loaded with oxidants from decades or millennia of radiation exposure, starts moving sideways, laterally, pooling toward the center of the sinking zone. It gathers there until it reaches a critical mass, and then it, too, begins to sink. Down at the bottom of the shell, all of this material, surface ice included, settles into a layer roughly 1 to 2 kilometers thick, sitting directly against the warm, convecting interior of the moon, against the boundary of Europa's ocean. The shape this whole process traces out, in cross-section, resembles something geologists studying Earth's own mountain roots have described before: a plume with a head and a tail, slowly, completely draining the dense material above it into the depths below. Here's where the study produced its strangest and most counterintuitive result, the kind of finding that makes scientists go back and recheck their own model. You'd assume that a bigger patch of weak, salty ice would mean more surface disruption at its edges, more of the surrounding, ordinary ice getting pulled in and destroyed along the boundary. Green and Cooper found the opposite. As the size of the sinking patch increased, movement at its outer edge actually decreased, dropping by roughly half across the range of sizes they tested. The reason turns out to be a kind of self-locking mechanism. As the drip forms, warm material flowing underneath the weak zone gets pulled sideways and shoved under thrust, in the paper's terminology, beneath the edge of the surrounding rigid ice. That under thrusting effectively welds the boundary in place, pinning the edges of the sinking zone even as its interior keeps collapsing downward. The result is a tug-of-war written directly into the ice itself. The edges get locked down, the center keeps sinking, and the ice, caught in between, gets stretched thin in some of the models, down to a single kilometer or less, creating a zone of active thinning and extension right at the margin of the drip. If this is really happening on Europa, It means some of the Moon's strangest surface features, the regions scientists already suspected were sites of active convergence, might have a visible signature. Locked. Static boundaries surrounding actively thinning ice. A pattern this model predicts almost as a fingerprint. Green and Cooper didn't stop at proving the concept could work under generous conditions. They asked a harder question. What's the least amount of salt this process actually needs? They reran the simulation, this time without artificially building in a pre-thickened, ready-to-fall patch of weak ice, letting the instability develop naturally instead. And they dialed the salt content down, 10%, 5%, 2%. At 1% salt by volume, a genuinely small amount, the process still worked. Every single test case, across the full range of conditions they tried, resulted in surface material successfully reaching the base of the shell, typically within 1 to 7 million years for the naturally developing cases, and even faster when a pre-thickened patch was already present. They also ran a deliberate control case, a null hypothesis, using ice that was extremely dense but completely undamaged. Undamaged, meaning none of the weakening effects of repeated tidal stress had been applied. Even with density cranked up to a physically unrealistic extreme, that undamaged ice failed to sink in any meaningful time frame. Its estimated descent would have taken well over 100 million years, far longer than Europa's entire surface history. In other words, density alone isn't enough. It's the combination of being heavy and being weakened that makes the ice fall. Salt without damage just sits there. Salt with damage drips. That distinction matters, because based on existing estimates of Europa's ocean salinity, the near-surface ice on the real Moon is thought to contain somewhere in the range of 1 to 14 parts per thousand salt, with theoretical near-surface concentrations reaching as high as 28 parts per thousand in some models comfortably within, or even below, the threshold this study found sufficient to trigger the process, assuming the tidal weakening is also present, and given how relentlessly and continuously Europa is flexed by Jupiter's gravity, that weakening condition may be met more often than not. There was also a second layer to this test. Rather than always starting with an artificially pre-built thick patch of weak ice, Green and Cooper let some of their models develop the instability naturally, from a uniform starting layer with no head start at all. In the most heavily weakened of these natural cases, something unexpected happened. Instead of one clean drip forming, multiple smaller drips broke off simultaneously along the base of the ice, competing with each other and briefly stretching the surface outward before eventually consolidating into a single larger sinking mass. Ice that was only lightly weakened, by contrast, tended to form just one single, well-organized drip from the very start, and, counterintuitively, that single clean drip sometimes reached the bottom of the shell faster than the messier multi-drip cases, despite having less initial weakening to work with. Even in the least favorable configuration, tested minimal weakening, minimal salt, no pre-existing thick patch at all, the surface ice still reached the base of the shell within about 15 million years. Comfortably inside Europa's known surface age of 40 to 90 million years, with room to spare. It helps to place Europa's proposed behavior against its neighbors, because viscous, flowing ice is not unique to this one moon, but Europa may be doing something with it that few others are. On Ganymede, the largest moon in the solar system, viscous relaxation and slow creep in the ice are thought to have shaped its distinctive grooved terrain. On Miranda, one of Uranus's smaller moons, similarly soft ice is believed to have produced strange, folded features called coronae, in a shell where the contrast in strength between weak and strong ice may have been even more extreme than what Green and Cooper modeled for Europa. Farther out, in the Kuiper belt, both Triton's oddly textured Cantaloupe terrain and Pluto's vast nitrogen ice plain, Sputnik Planitia, show signs of active or ancient surface convection, although Pluto's case involves nitrogen ice rather than water ice, a genuinely different material with its own separate behavior. Meanwhile, Callisto and Mimas, two icy moons roughly comparable in size and temperature to Europa, appear to show none of this. Their surfaces are old, heavily cratered, and largely undisturbed evidence, by contrast, that flowing, self-recycling ice is not a given just because a moon happens to be cold and made of water. Something specific to Europa's situation, whether that's the intensity of its tidal flexing, the salinity of its ice, or some combination of the two, appears to be doing the work. Europa's own crater record backs this up. Its two largest impact basins, called Tyre and Callanish, appear strikingly flattened and smoothed out compared to similarly sized craters found on Callisto or Mimas, a sign that whatever process is active in Europa's shell has had enough time and enough strength to visibly erase the scars of ancient impacts, something the older, quieter ice of its neighboring moons simply hasn't experienced. If Green and Cooper's proposed mechanism turns out to reflect what's genuinely happening inside Europa's ice, the implications reach further than just one moon. For Europa specifically, the researchers estimated what this process could mean for oxygen delivery to the ocean. Using published estimates of Europa's total surface oxidant inventory, they calculated that a single drip event, roughly 15 kilometers across, could deliver an amount of oxygen to the ocean that in the fastest sinking scenarios comes close to matching the threshold flux researchers believe is needed to keep Europa's ocean chemically active enough to support simple life, rather than settling into inert equilibrium. In the slower scenarios, meeting that same threshold would require a much larger share of the moon's surface to be recycled this way over time. The uncertainty here is still enormous by the researchers' own estimate, spanning several orders of magnitude, but the fact that the numbers land anywhere in the same ballpark as habitability thresholds is itself notable. The idea may also reach beyond Europa. The researchers point out that similar viscous foundering has already been proposed to explain smooth plains found on Pluto and its moon Charon, discovered by NASA's New Horizons mission. And they speculate that something related, though working through slightly different physics, might help explain a genuine long-standing puzzle on Saturn's moon Titan, why so little ethane accumulates on a surface that should, based on its atmospheric chemistry, be steadily producing it. If icy foundering is quietly recycling surface material into Titan's interior, it could be pulling that ethane down and out of sight. But the researchers themselves are careful, cautious, even about how far to take this. They call the work a preliminary proof-of-concept study. They openly acknowledge that their model leaves out several complications. The melting that would likely occur once salty ice reaches warmer depths, the way salt-enriched ice might be layered rather than uniform, and the behavior of a free-moving surface rather than the simplified boundary they used. Some researchers argue this same convergence process could instead resemble Earth-style plate subduction. The paper suggests the two processes might even work together rather than as competitors. What they conclude, in plain terms, is this. For the conditions they modeled, salt-driven icy dripping is physically viable, not proven to be happening, not confirmed by direct observation. Viable, meaning the physics holds together, meaning it's a real candidate, meaning it deserves to be taken seriously alongside cracks, convection, and brine percolation as one of the possible ways Europa's surface secrets make it down into the dark. If Europa's ocean really is exchanging material with the surface, in either direction, you'd expect the ice to carry some fingerprint of what's happening down there, and it does. Spectroscopic observations from the Hubble Space Telescope have picked up an absorption signature in Europa's chaos regions, consistent with irradiated sodium chloride crystals, ordinary table salt, effectively altered by exposure to radiation, sitting in areas thought to correspond to recent upwelling from below. Separately, infrared data has revealed a weak but real absorption feature consistent with ammonia, concentrated along Europa's linear surface features, suggesting it too was recently carried upward through cryovolcanic activity or something similar. Ammonia matters here for a specific reason. Mixed into water, it can significantly lower the freezing point of the ocean, which would mean a thicker, colder-tolerant liquid layer than plain salt water alone would allow. There's also a broader story hiding in the ocean's likely history. Models suggest Europa's ocean may have started out considerably more acidic than it is today, rich in dissolved sulfate, calcium, and carbon dioxide. Over the roughly 4.5 billion years since, that same modeling suggests the ocean's chemistry may have gradually shifted towards something dominated by chloride instead, inching, chemically, toward a composition not unlike Earth's own oceans, which are famously about 1.94% chloride by weight. None of this proves anything about the dripping process specifically, but it does something almost as valuable. It confirms that surface and ocean chemistry are connected at all, that whatever the ice looks like on top carries real information about what the water below is doing. Green and Cooper's proposed mechanism doesn't have to invent that connection. It just has to explain one more way it might be happening. There's one more thread in this story worth including, mostly because it shows how unsettled even the most exciting Europa findings can turn out to be. In 2012, the Hubble Space Telescope captured an image interpreted as a plume of water vapor erupting from near Europa's south pole, potentially reaching more than 200 kilometers high, more than 20 times the height of Mount Everest. If real, it would mean Europa was doing something similar to Saturn's moon, Enceladus, which is known to actively vent material from its subsurface ocean directly into space, offering a way to sample an alien ocean without ever having to land or drill. Additional Hubble observations in 2016 seemed to offer some support. Then, in 2018, a reanalysis of decades-old data from the Galileo spacecraft suggested that during a 1997 flyby, Galileo may have unknowingly passed directly through one of these plumes, detecting disturbances in Europa's local magnetic field and plasma environment consistent with a burst of water vapor. But the picture didn't stay settled for long. Later modeling work suggested that if plumes exist at all, they're likely far smaller and more episodic than the 2012 observation implied. And in 2026, a new paper examining the evidence found no confirmed sign of localized water vapor at Europa at all, proposing that earlier detections may have resulted from nothing more exotic than slightly inaccurate positioning of Europa's disk in the telescope images used to make the original claim. So, as of now, the plumes remain unconfirmed, not disproven. Unconfirmed. It's a useful reminder of how this entire field operates. Exciting signals appear, get tested, sometimes hold up, and sometimes quietly dissolve under closer scrutiny. The dripping mechanism proposed by Green and Cooper hasn't been tested against real observational data yet at all. It exists, for now, purely as a successful computer model. Whether it holds up the way the ocean itself has, or fades the way the plumes might be fading, is something only future missions will be able to say. It's worth sitting, for a moment, with how much of this remains genuinely uncertain. We don't know the actual thickness of Europa's ice shell. Estimates still range from a few kilometers to several tens of kilometers. We don't know exactly how salty the real ice is at different depths and locations, only that models suggest it should be somewhere in a certain range. We don't know whether the specific process Green and Cooper modeled is actually occurring on Europa today, has occurred in the past, or will ever be directly observed. Recent modeling published in 2026 has even suggested that Europa's rocky seafloor may currently be too geologically quiet, too tectonically inactive to generate the kind of high-energy hydrothermal systems long imagined as an ideal environment for life, meaning that whatever chemical exchange is happening between surface and ocean may need to matter even more than previously assumed. That's the layered nature of this mystery. Every answer opens onto another open question. The oxidants are there. The ocean is there. The heat is there. What's contested isn't whether the ingredients exist, it's whether and how quickly they ever actually meet. Even the basic question of how thick Europa's ice shell is remains split between two competing pictures. The thick ice model, favored by most geologists who study Europa's largest craters, puts the solid crust somewhere between 10 and 30 kilometers, with a ductile, warm ice layer underneath that could push the total water ice layer to around 100 kilometers before you reach the rocky interior. The thin ice model, based on how the crust flexes under Jupiter's tides, suggests the elastic, rigid portion could be as thin as 200 meters in places, thin enough that direct, repeated contact between ocean and surface might not be a rare event at all, but something closer to routine. Green and Cooper's simulations were built around the thicker end of that range. If the real shell is thinner in places, the physics of dripping would likely still apply, just over an even shorter path, and likely an even shorter time. This is precisely the question NASA's Europa Clipper spacecraft, still years from arrival, was built to help answer. It isn't the first spacecraft to visit this moon. Pioneer 10 captured the first distant images of Europa in 1973. The two Voyager probes passed through the system in 1979, close enough to first suggest the possibility of an ocean beneath the ice. Galileo spent 8 years, from 1995 to 2003, gathering the magnetic field data and close-up imagery that turned that possibility into a serious hypothesis. In September of 2022, Juno swept past at just over 200 miles, capturing some of the most detailed images of the surface to date. Europa Clipper is different from all of them. Having launched in October of 2024 and used gravity assists from Mars and Earth to slingshot itself toward the outer solar system, it's scheduled to enter orbit around Jupiter in April of 2030, not to orbit Europa directly, where radiation levels would destroy it within months, but to loop around Jupiter itself and dive in for repeated close passes, dozens of them over several years, coming as near as 16 miles above Europa's surface during the closest approaches. It carries 9 science instruments built specifically to attack this exact problem. An ice-penetrating radar designed to see straight through the shell to the ocean below, a magnetometer to refine what Galileo first detected, a mass spectrometer sensitive enough to identify the chemical signature of anything drifting off the surface, and cameras capable of mapping nearly the entire moon in a resolution better than anything gathered before. None of Clipper's instruments are built to detect life directly. That was a deliberate choice. You cannot point a spacecraft at an unexplored ocean and simply ask it to find something living. What you can do is ask smaller, answerable questions. How thick is the ice? Does the ocean touch the rock below? Is surface material actually making its way down? And let those answers tell you whether the bigger question is even worth continuing to ask. Which brings the story back to where it started. A small patch of ice, somewhere on a moon 400 million miles away, that might be a little saltier and a little weaker than the ice around it. Nothing about it would look unusual from orbit. No plume, no crack, no visible motion at all on any timescale a camera could capture in a single flyby. Just ice, quietly and invisibly rearranging itself, carrying a few thousand or a few million years worth of sunlight-starved chemistry on a slow, silent fall toward an ocean that has never once seen the sun. We built the model, we ran the simulation, we watched the numbers converge on something physically possible. We have not yet watched it happen. And somewhere underneath one of the smoothest, quietest surfaces in the entire solar system, it's possible that we already have, we just don't know where to look.